Electrical safety can be tricky, so we're going to look at some of the issues that are specific to Formula Hybrid, as well as general electrical safety issues. One issue that you hope you'll never encounter, but you want to be prepared for in case it does happen, is what to do if a vehicle is smoking or on fire. You want to immediately begin verbal notification of the fire and evacuate the area. If it's safe to do so, and this is a big if, you can activate the big red buttons to shut down the tractive system. Also, with a big if it's safe to do so, if the vehicle's in the garage, you can attempt to move it outside, but only if you can really safely get close to the vehicle to do that. And if the vehicle has ultracapacitors, they have particularly toxic smoke, so you don't want to attempt to move it, but simply leave the area. In any case, activate 911 from a cellular device and advise of a fire located at the New Hampshire Motor Speedway, that's 1122 Route 106 North in Loudon, New Hampshire. And most importantly, give them a specific location. For example, the infield inside the north garage. The complex is huge, so first of all, that we're in the infield and then specifically at the north garage is really important information. For fires that don't involve lithium-ion batteries, you can make a single brief attempt to extinguish it with one of the handheld portable extinguishers while you're waiting the arrival of trained personnel with better gear. But if it's a lithium-ion fire, you're not going to put it out with one of those extinguishers anyway, so it's more about keeping safe and keeping people away from the vehicle. What if somebody's injured? During the dynamic events, there will be an ambulance and EMTs on site. So you would send a runner to get the ambulance or the EMTs. You would also, in the case of ventricular fibrillation from an electrical shock, send a runner to obtain an AED and apply CPR until the AED is right there available and ready to go. Call 911, and in most situations, don't attempt to move an injured person. Leave that to the EMTs. One possible exception to that is if someone is in contact with high voltage. Still, you wouldn't just grab them. You would make sure you had an electrical insulator between you and the victim, or better yet, shut down the electrical system and remove that hazard. In the case of ventricular fibrillation, your brain is no longer getting oxygen, and that's a really serious situation. Within 1 minute, brain cells will start to die, but survival is possible. 3 minutes, you have serious brain damage. 10 minutes, and the patient is unlikely to recover. 15 minutes, and it's pretty much impossible. So time is of the essence, and that's one of the reasons we have automated emergency defibrillators around the site. These are marked on the facilities map that you will get at check-in, and you don't need to be trained to use these devices. They have really clear, easy to follow instructions with the unit. But you don't want to say, okay, that's going to take care of it. If you can find someone who knows CPR, you want to do that even for just the short time until someone gets there with this defibrillator. We have high voltage warning lights that are available to demarcate a region where people are working on exposed high voltage. You should almost never use these. You should minimize work with exposed high voltage, and you should not just turn it on just in case some high voltage becomes exposed. You want to save this for those rare situations in which you're actually exposing the high voltage, and you need to do that, and you're carefully controlling the area. You want to have this light on. We shouldn't look around and see these lights on very much at all. So whose job is this safety stuff? A bunch of you are mechanical engineers. Why are we talking about electricity? Well, You might get involved in electrical systems. Interdisciplinary engineering is more and more common. But even if you're not doing that, you will be working around high voltage to install other kinds of mechanical components. And even if it's not you working on the electrical stuff, if you're there, you might be the one who has to respond. So safety is really everybody's job. You're responsible for your safety and for everybody around you. So what's the number one rule? The number one rule is never work alone. And, there's okay. I was afraid I was alone for a minute there, but there's the rest of my crew. So you want to have people with you, both to help in the case of an emergency and to prevent you from doing something stupid. Working with high voltage is very different from working in a circuits lab at school. For one thing, the experiment isn't designed ahead of time for you, but also the voltages are lethal. And an electrical engineering program doesn't necessarily teach you really anything about electrical safety. And some of you aren't electrical engineers at all, so we'll start with Electrical Engineering 101, which is Ohm's law. The current I is the voltage divided by the resistance. And for safety considerations, that resistance might be body resistance. Typically 100 kiloohms for dry skin to 1 kiloohm for wet skin. And so, for example, if we plug those numbers into that formula, we would get 1 milliamp for dry skin to 100 milliamps per wet skin with a 100-volt voltage source. And that's with your skin intact. If you scraped your knuckles, any kind of cut in your skin can dramatically reduce that resistance. These are calculations that are just for the general idea of it. This is not supposed to be how you certify that what you're going to touch is safe. So what are the effects of this current that I said was from 1 milliamp to 100 milliamps in that example case? Well, at 1 milliamp, you get a little bit of a tingle, nothing dangerous. 5 milliamps, you'll probably feel that. It's not super painful, but it's enough that it can give you either an involuntary muscle spasm or just from surprise, you might jump. And that can either mean that you then get into a worse shock, or maybe you trip and fall and hurt yourself another way. So that already can carry some danger. By the time you get to 10 milliamps, that's going to be more painful, and more importantly, you can lose muscle control. And this is the range where you might not be able to move your hand away. Worse, you might be grabbing on and not able to let go in order to move your hand away. When you get to 30 milliamps, that can cause respiratory paralysis. That means that you stop breathing. And then somewhere around 75 milliamps is where ventricular fibrillation can happen. That means that your heart the electrical signals are disrupted and it's no longer pumping blood effectively, which is why that's so dangerous. So these numbers are really small compared to the currents that you might carry in a big wire like that above my head, and yet they're still dangerous. And one of the things that means is that if you have high voltage wires, you might notice a big wire like that and think, yeah, that's scary. But a little wire like that can be just as dangerous. It's really the fact that it's a high voltage wire that makes it dangerous. The pocket rule is really important. Every engineer should carry a pocket rule. Oh, not that kind of pocket rule? Yeah, so this one is a non-conductive pocket rule, folds out, measures in centimeters, much more appropriate for electrical. Oh, not that kind of pocket rule either. Okay, this pocket rule is that if you're working near high voltage, the most dangerous thing is to have both of your hands touching two different potentials and have the current go through your heart. So what you want to do is pick one of your hands, put that hand in your back pocket, and that will just keep you from unthinkingly putting that hand somewhere that you shouldn't, you're then just working with one hand. You know that that hand isn't going to, you might bridge two things with your fingers, but it's not going to carry current through your heart. Okay, now electrical engineering 102, power. If we have a current and a voltage and a resistance, we can calculate power as I squared R or V squared over R. And so if we have the total amount of heat energy generated during an interval delta t, we can write that as the power times delta t, or V squared times delta t divided by R. If we have a short circuit with a high voltage system, we have a big V that's squared, a small r on the bottom, and so we're going to have very high energy. That high energy situation is called arc flash. It can vaporize copper. It can burn your skin very rapidly. That causes a lot of electrical injuries, can cause very severe burning. The explosiveness of it is dramatic. Copper expands 1,000 times when it's vaporized and carries a lot of heat energy with it. So here are some of the results of that. I'm going to hide my eyes from this, but show you guys this. I don't want to see this, but I think you need to. Okay, everybody seen that? That's what can happen from arc flash. Now I think it's safe to uncover my eyes again. So, how do we avoid these good electrical safety practices? The pocket rule, one hand in a pocket that is. A lockout tagout procedure to make sure that your high voltage system is off either when you're working on it or when nobody's there and nobody should be working on it. Use non-conductive tools when you're working on or around high voltage systems. They're not just for electrical engineers. You might be working near that and want to use those non-conductive tools. You want to keep the high voltage working area neat, organized, and that's to prevent trip hazards because, well, you can hurt yourself tripping, but particularly tripping and falling into high voltage is not something that you want to risk. More safety practices in the paddock. Use cones and chain to set up a high voltage area if you are working with high voltage. Find a limited access storage area if you need to store an energized high voltage system, say a battery pack, something like that. You want to transport components on carts, not by hand. You want to cover them, cover any exposed voltage with an insulating blanket. And you want to keep high voltage systems away from welding, grinding, or other metal work. Those little metal pieces can cause your system to fault and be a really difficult thing to find. Safety glasses you should be wearing whenever you're within 10 feet of work going on a vehicle, and that includes mechanical or electrical work. High voltage gloves are a two-part system. There's a leather overglove over the actual insulation, which is the rubber glove underneath. When you're using those, you want to give them a quick inspection every time you use them, and you want to use them whenever you're working on high voltage. They come in different sizes. Those are a little big for me, but you can get the right size for you. They should be tested every 12 months. Typically, companies will rotate them every 6 months to make sure that we always have tested, up-to-date gloves on hand. Other safety equipment includes 2 dry chemical fire extinguishers, chemical spill absorbent, high voltage insulating blankets, large enough to cover the accumulators whenever they're open. Material safety data sheets for anything that might be dangerous, and face shield and any other equipment that's required by the MSDS. The high voltage electrical systems in Formula Hybrid and in most modern electric and hybrid vehicles are a fully isolated system. And that's different from typical building wiring. The idea of it is that the high voltage system in this box is completely floating. There's no connection to the ground, which is the frame. And that means that for a hazard to occur, you need two faults. And that means that when the first fault occurs, this insulation monitoring device can detect that fault and disconnect things before it actually hurts anybody. One feature to be aware of in this is that because it's fully isolated, both ends of the battery are equally dangerous. It's not that this is the low voltage end and that's okay, and up there is the high voltage end and that's what you have to look out for. Both of them are equally dangerous, and in the case that something goes wrong, either one could be different from ground and could be dangerous. So we treat both of those, everything inside that box, as potentially dangerous, and we make sure that no hazard occurs by keeping it isolated and monitoring that isolation. So a good high voltage electric system has that insulation monitoring. It also has strict segregation of high voltage and low voltage wiring. It's run in separate conduit, routed separately inside boxes where it's separated by insulation or by adequate spacing, either through the air or printed circuit boards. There are no conductive penetrations through the accumulator container. That's particularly important because even after these switches open, there's still voltage inside the battery itself. Any conductive or metal parts on the body or in the vehicle are grounded to the chassis. So everything outside of that box that's conductive is all referenced to this frame. That makes sure that the insulation monitoring device can detect any problem, and that when there isn't a problem, none of that stuff can be live or dangerous. When we shut down the high voltage system, the way that's normally done is with these isolation relays, accumulator isolation relays, AIRs, and any big red button or any other kind of fault will open two of those, one at the plus and one at the minus. It's important to realize, though, that those can fail. The contacts, when they connect, it's possible for them to weld and get permanently connected, permanently on or closed. So we should never assume that the high voltage is safely turned off without verifying it somehow. We also have fuses. Fuses are rated for the continuous current rating of the wire or conductor that it protects. So it's not based on how much current you expect, it's based on how much current that wire can safely handle, and make sure that the fuse will blow before the wire burns up. You should have a set of high voltage safety procedures. That includes steps to energize, de-energize the vehicle, additional steps if you're going to work on the electrical system or if it has been worked on to verify that it's okay. Things like measuring resistances with a multimeter to make sure that connections are correct, announcing when you're going to turn on the contactors, avoiding extra people around the car when you're doing things like that. This should all be in a document that everyone agrees on and understands and follows. One consideration is to know, when does it stop being treated as high voltage? If you have a scrap of wire on the ground that's not connected to anything, you can touch that. It's not live. But like these wires above my head, are they safe to touch? Well, we don't know yet. So always assume it's live until you've verified that it's not. And that includes if you go away from the vehicle, it was not live before, when you come back, you want to verify it again. So how do you do that? Well, you use a 3-step test. So I take my meter, turn it on, and the first thing I do is not to actually make a measurement of the wires I'm interested in. The first thing I do is make sure that my meter's working. And the way I do that is I take a known live voltage, doesn't have to be a high voltage, just some known live voltage, like the voltage on this 12-volt battery here. I probe that and I make sure that my meter is reading an appropriate reading. meaning that the meter is working. So now I can probe the voltage that I'm interested in. I want to check that those wires above my head aren't live, so I probe them and then check that the meter reading is 0 when I'm probing them. You might think that then you're done. You know the meter's working, you check the wires, but there's one more step. We have to probe the known live voltage again to make sure the meter's still working, that it didn't just quit between those steps. This seems a little bit like overkill, but I've seen people in a situation where they would have touched high voltage if they didn't take all those steps. I trust my meter. It's a good meter. I like it. No offense to my meter, but I'm not going to trust my life to it. I'm going to check it. The high voltage shutdown works with the big red buttons. Those are on the sides of the vehicle as shown up there and on the dashboard. There's also a bunch of other ways that it can be shut off. There's a brake over travel switch if the brake fails. There's an accumulator monitoring system, battery or ultracapacitor. There's the insulation monitoring device, or IMD, that checks that we have the fully isolated system. There are also the master switches, and on some vehicles, there are interlocks for wheel motors if you have in-wheel motors. There's a tractive system active light that tells you when the tractive system is active. It's a light like that mounted under the roll hoop. It must be on whenever the voltage outside the accumulator exceeds 32 volts or 1/3 of the maximum bus voltage, whichever is higher. And that has to be directly controlled by the tractive system voltage being outside the accumulator. Not measuring what you're feeding to the relays, but what's actually happening in the system. But there should be no tractive system voltage at that light itself. There's also a safety system OK light, and that's on either side of the roll bar near the shutdown buttons. The vehicle's not allowed to run if that's not illuminated. That tells us that your safety systems are working properly and that they haven't detected a serious safety hazard, such as the accumulator monitoring system or the isolation monitoring system detecting a fault, also the big red buttons, or the brake over travel switch. But if you turn off the high voltage system with the big red button in the cockpit, that's going to leave this active. And that means that the driver can turn off the tractive system for safety reasons whenever they want without worrying that that's going to indicate a fault and knock them out of the race. Physical protection for high voltage wiring is required. It needs to either be in orange UL listed non-metallic conduit as shown above, or in approved orange shielded double insulated cable. Or it can also be in specifically marked high voltage enclosures. It needs to have conduit fittings at joints to provide strain relief for 45 pounds of force. That's so that if one of those conduits gets yanked on, you're yanking on that conduit fitting, not ripping the wire out and having exposed wire ends. High voltage and low voltage are never in the same conduit, and when they're in the same enclosure, they're strictly separated. All exposed conductive parts of high voltage enclosures, such as heat sinks or body panels, have to be grounded. And all insulation materials need to be rated for the voltage and for the temperature of operation. No saran wrap. Finally, warning labels are required, not just for the sake of having warning labels, but because first responders will need to know which parts of the vehicle are dangerous if they're rescuing the driver. So those need to be clearly visible to anybody approaching the vehicle. I'm not delivering this live to be able to take your questions immediately, but I and lots of other people at Formula Hybrid are happy to have your questions, happy to help you with this.